Welcome to lecture number 25 of the course on nonlinear structural analysis, theory and applications. Let us recall what we have done in the previous lecture. So, in the previous lecture, we discussed a procedure that you can use to compute the moment curvature response of any cross sections. So, the idea is you have a cross section, be it a rectangular, be it wide flange, be it any other type of section. For the time being, we are talking about steel cross section, right. So, what you do, you discretize it into number of fibers and each fiber is associated with a stress strain response, right. And then what you do, you apply some curvature, okay, and calculate the strain at each fiber and do the state determination. That means, determine the stresses at each fiber and then integrate them along the depth of the cross section and then determine the bending moment. Of course, you have to satisfy that the axial force is 0, or if you have axial force, then the computed axial force minus the axial force that you have applied, that the difference should be within an acceptable tolerance, right. So, once we have done that, then we have looked at the moment curvature response of rectangular steel section under monotonic as well as cyclic loading. And we showed you that when you take a rectangular section, okay, need not be rectangular, but any other section as well, when you go past the yield moment, okay, and then you unload, what happens? You unload elastically and you are on the x axis. That means, the curvature, there will be some residual curvature, but the moment is 0, right. At that point, that there are no bending moment acting, but you still have some residual curvature which causes strain along the depth of the cross section, and then you will have residual stresses. Remember that the residual stress distribution must be such that the resultant of the stresses must be equal to 0. That means, there should not be any axial force and should not be any bending moment. So, it is a self equilibrating stress distribution. Okay. In this lecture, what we will do? We will look at monotonic and cyclic moment curvature response of I sections. In the United States, they call these sections wide flange sections. Okay. And then we will get into the idea of analyzing cross sections in the presence of axial force. What happens if you have axial force as well as bending moment? Okay. And that means, we are now getting into the PM interaction. Okay. So, in this lecture, we will talk about PM interaction for rectangular sections and also look at the codal provision. Okay. So, let us get started with the moment curvature for I sections. Okay. So, the first example I have here is an I section which is shown here. Okay. So, just for the notation, this width of the flange is denoted by BF, the overall depth of the section is denoted by H, and the thickness of the wave is TW, thickness of the flange is TF. Okay. Like we did for the rectangular section, here also we have to discretize each of this element into number of fibers. So, as you can see here, the flange is divided into 3 fibers. So, NF, number of fiber in flange, in each flange is 3, what I am showing on the using this schematic. Okay. And in the wave, I have used 10 fibers. This is 1, 2, 3 up to 10. Okay. This is for the demonstration, and this is my local y axis, this is my local z axis. So, local x axis is pointing towards us. Okay. And each fiber, as I am showing schematically, is defined by the stress strain response. Okay. In this case, I am showing a bilinear plastic response, where alpha is the strain hardening ratio. Okay. You can set it equal to some value, or you can make that equal to 0. Okay. So, for this example, what I have done, I have taken this NPB 550 by 210 by 92.07 section, which is coming out of IS 12778 2004. Okay. So, this is narrow parallel beam section, this is the nominal depth, this is the nominal width of the flange, and this is the weight per unit run in kg. Okay. Let me go back to the code and show you this cross section. This is the code IS 12778 2004. Okay. And the notation they use in the code is slightly different from what I am using. For example, the overall depth is d, the thickness of flange is capital T, thickness of wave is little t, and so on. Okay. So, the cross section that I have taken is this NPB 550 by 210 by 92.07. So, let me go to that particular section. This is the one that I have chosen, okay, the highlighted one, right. Okay. So, as you can see, the depth is, the 550 is the nominal depth, actual depth is 547, B is the nominal width, which is actual width in this particular case, thickness of the wave is 9 and thickness of the flange is 15.7 millimeter. And note that this R is the root radius. So, basically in the actual section there is a fillet here, okay, right. So, that R is that radius. Now, in the analysis what we will do, we will ignore that and we will treat that these are composed of rectangular elements. Okay. So, I have noted down the numbers and I have done this analysis in OpenSeas, which I will show you. There I have used number of fiber in the wave equal to 20 and number of fiber in the flange 5, and I have used strain hardening ratio is equal to alpha is equal to 0. So, that means this is elastic, perfectly plastic. Okay. And these are the ZE, the elastic section modulus, the plastic section modulus, and you can compute My and Mp if you take, in this case what I have taken sigma y is equal to 250 MPa. So, for this E250 steel, then this is the yield moment and this is the plastic bending moment. And as you can see, I will take you to OpenSeas and show you how this is done. Okay, I am plotting the normalized moment M by My, okay, with the normalized curvature phi by phi y. So, this is the response under monotonically increasing curvature, the moment curvature response, okay, and this is the one for a rectangular section. And as you can see, what is this number? This number is actually equal to your shape factor, okay, which you will see when I go to the OpenSeas. So, right now the axial force I am setting it to 0, Fy is 250, E is 200 GPa, all are in Newton and millimeter unit, alpha is 0. So, this is the NPB section, okay, and coming from this code as I showed you, right. And then these are the values of moment of inertia, the elastic section modulus and the plastic section modulus coming directly from the code, right. Now, these numbers are slightly different from the calculated values of I, Jd and Zp. Why? Because as I was discussing, this fillet is neglected in this analysis that I will be doing in OpenSeas, okay. But the values given in the code, okay, these numbers here actually include that effect of the fillet. So, therefore, these numbers are slightly different from the numbers that you would get if you assume that the section is made of rectangular elements. Okay. So, now here I am also calculating My code, Ze code into Fy just to show you the difference. For example, if you see yield moment using Zd from the code is 548.25 kilonewton meter, whereas the yield moment if you assume it to be consisting of rectangular element is 519.45. So, there is a little bit of difference. Similarly, the plastic moment using Zp from code is 618.7, whereas plastic moment computed by hand calculation using rectangular elements is 587.46 kilonewton meter. What about the yield curvature? Well, the yield curvature will not change. Okay? You can try that whether you consider the My from the code or you consider the My from your hand calculation, the yield curvature will not change. Why? Because what is yield curvature? So, yield curvature is equal to the yield moment divided by Ei, right. Now, My is Ze into sigma y and Ei is basically I, Zd is what? Zd is I divided by h by 2. Okay. So, you can write I is equal to Ze into h by 2. So, this Zd will cancel and h is the same whether you take it from the code or whatever I am using, basically it is the same number, right. So, therefore, yield curvature will not change, but your My and Mp will be slightly different from your hand computation. Okay. Then what I am doing, I am saying okay, I will divide this yield curvature into 100 increments and then I will apply a maximum curvature of 10 times the yield curvature, right. So, the maximum curvature that I am applying is 0.0457 1 by meter. Okay. So, this is monotonically increasing curvature. The remaining procedure remains the same as the previous example of a rectangular cross section. The only change will be here. Now, in the previous example for rectangular section, we had to discretize it using the patch rectangular command, but for wide flange section, like I said, our I section in the US they call it wide flange section. So, there is a command called WF section 2D. Okay. Using this command, all you have to say is okay, what is the section tag? This is 1, material tag, this is 1, I am using steel 01 material. What is the depth of the cross section, thickness of wave, the width of flange, thickness of flange, number of fibers in the wave and number of fiber in the flange. Then it will do the automatic discretization that I was showing here. Okay. Then this is done, the rest of the procedure remains the same as before, 0 length section. So, this is the section tag that we have, the section that we have just now created, WF section 2D, and then you apply the axial force. In this case, it is 0, P is 0 as I have shown earlier. Okay. And if you have axial force, of course, you have to do a static analysis with the axial force, and then, so that is what is done here, and then you apply a reference moment, which is this, and apply incremental curvature. So, these are the recorders same as before. So, here I am applying the incremental curvature. So, displacement control at node 2 in 3 direction, that means the rotation direction, and this is the incremental curvature that I am applying. Okay. So, finally, you get the moment curvature response. What is the maximum moment? 586.7 kilonewton meter. And what is the computed MP? If you look at the computed MP, that is 587.46, and here in the result what I got 586.7. They are very close. So, if you keep on pushing it further, applying more and more curvature, eventually you will get the same number. And of course, you may have to increase the number of fibers to be able to get the exactly same value, right. So, this is close enough, right. Okay. So, what I have then done, I have normalized this moment curvature response, what I showed you earlier, okay, and comparing with the rectangular section. As you can see, this rectangular section takes more curvature to reach the MP, whereas the I section reaches the MP at a faster rate, okay, which we have already discussed earlier, right. Now, if you look at the stress strain response at 3 different locations, what I am doing? I am looking at the stress strain response here, here, and then somewhere at quarter depth at these 4 locations, right. As you expect that this is at y is equal to 273.5, that means here what you see that this has yielded in compression, that is what we expect. Okay. And near the extreme bottom fiber, this has again yielded in tension. Okay. And then at around h by 4 from top, that also yielded, okay, because we have applied enough curvature, right, and similarly this one. Okay. Now, when I do the cyclic one and unload it, okay, after applying some curvature, we will see that there will be residual stresses as we have seen for rectangular section. So, let me show you that. So, what I have done, I have taken the same cross section, right, where this 92.07, just to show you one more time, is this is the unit weight, okay, 92.07 kg per meter run. Okay. So, 550 by 210 by 92.07, the same cross section. What I have done, I have applied this much of curvature, right, and then when I am unloading, the unloading is elastic, right, because every fiber is unloading elastically. So, the moment curvature response must unload elastically. So, at this stage you have this much of curvature, that is residual, right, and from here to here this is your elastic curvature that you have recovered, isn't it. So, because of this residual curvature, there will be residual strains along the depth of the cross section and there will be residual stresses. So, for example, let us talk about this fiber which is at plus h minus t fiber by 2, that means it is here, okay, at the centroid of this fiber, right. So, when I apply bending moment, this is developing compressive stress, right. You come here and then you unload elastically, right, and then it goes into tension. So, positive is tensile here. Okay. So, 31.11 MPa you have tensile stress. On the other hand, if you look at this fiber here, right, which was initially under tension, it goes like that, right, and you unload elastically. So, you come to minus 31.11. As you can see, this is kind of antisymmetric, right. Here you have 31.11, here you have minus 31.11, okay. And at the quarter depth, this is 103.42, this is minus 103.42. This is to show you that there will be residual stresses. Now, in this case, what I have done, I have recorded only the stresses and strains at 4 locations. So, let me show you where I am doing the recording. So, here. So, I have recorded only at 4 locations, but if you want to record, it is possible you can record at all fiber locations and then at a given instant of time or at a given curvature, you can plot the distribution of stress and strain along the depth, and if you do that, you will get the distribution of residual stresses at the end when you have completely unloaded. Okay. Now, if you look at the curvature history, this is the history I have applied. Now, how do I know that I will come to this point so that I end up being here? Okay. So, what I have done, I am assuming that at this curvature I have reached pretty much the plastic moment, right, and then I know what is my EI, this slope is EI. So, then I know this point, I know the moment, I know the curvature that I have applied, I know EI. So, I can compute how much is this curvature, right. So, that is how I have defined this curvature history. Okay. And yeah, this is what I was showing, that I am recording at 4 different locations, but you can record at all fibers, right, and then you can get the distribution of stresses along the depth of the cross section instead of the stress strain response. Okay. That is about the cyclic response. Now, if you go back, let me show you one other thing. So, there are 2 different histories that I used in the previous class. So, let me also do that here. So, I will uncomment this and comment this out. Now, in the previous case, it was kind of a very smooth moment curvature hysteretic response, but in this case it will not be so much smooth because we are using elastic perfectly plastic material. And for a rectangular section, as you remember, the moment curvature is very smooth because there is MY to MP difference is 1.5. Here it is not so much, okay, because this is an I section, right. Okay. If I go to the previous example, I think somewhere I have computed what is the value of the theoretical shape factor. Yeah, the theoretical shape factor is 1.13, whereas the one computed from OpenSys is 1.13 to 1.129. So, pretty much the same, right. So, it reaches the MP much quicker, right. So, therefore, you get kind of sharp transition here. Now, what you can do, you can take this example, use Geoffroy-Menegotto-Pinto model which is still 0.2 and redo this example and see how the moment curvature response changes, and you can do it without isotropic hardening, you can do it with isotropic hardening, right. So, now let me go to the PM interaction for rectangular sections. So far what we have done, we have looked at rectangular cross section and wide flange cross sections without any axial force, right. So, if we apply axial force, let us say I have a member, I have applied some axial force, let it be compressive, it could be tensile as well. Now, I am applying some bending moment and I keep increasing the bending moment. What will happen? Eventually, the entire section will become fully plastic. Okay, and our assumption is that we are assuming elastic perfectly plastic material behavior, right. So, that means let us say if this is my bending moment and this is the axial force that I have applied on this rectangular cross section, okay, at some point after increasing the moment, okay, if you have applied axial force first and then increasing the moment, you let us say get a stress distribution like that. The entire section is plastic, or it can be done the other way also. You apply some bending moment and then keep increasing the axial force, eventually the entire section will yield, right, and you get a stress distribution like this, right. So, what is this? This is my plastic neutral axis under moment and axial force. So, what I want to do now, develop a relationship between this applied moment and this P, which is called the PM interaction. So, how do I do that? Well, this is the stress distribution, which I can say this is equal to this plus that. So, what I am doing? I am dividing this symmetrically. So, let us say whatever distance I have here, I take the same, and this is basically this resultant stress is my axial force, and then whatever is remaining, this one and this one, is going to give me the bending moment, and the depth of the neutral axis is denoted by y sub p. Okay. So, this is equal to this plus that. Now, I can write down the axial force. So, what is my axial force? Is the resultant of this stress distribution. What is this? This is equal to, if this is my yp, okay, then you can determine. So, I have done it on this side, right. From here to here is yp, that means this is d minus yp. So, that means this is also d minus yp. So, the total is d. So, then this has to be 2 yp minus d. So, that if you add all of them, then you get d, right. So, what is this axial force resultant due to this? That is b, the width, into sigma y into this 2 yp minus d. So, which I am rewriting like that. What is Py? Py is the yield strength under axial force. So, which is b into d into sigma y, right. Now, this equation I can rewrite like that. I want to determine yp as a function of p by py. Okay. Then what I am going to do? I am going to determine the bending moment. So, let us say this is my compressive resultant C and this is my tensile resultant T. Okay. So, what is C equal to? Well, C is equal to sigma y into d minus yp into, so d minus yp is this distance, right, and into b, right. Okay. Now, what is this distance from here to here? Well, this distance is equal to d minus yp, because this is acting, this is d minus yp by 2 and this is also d minus yp by 2. Okay. So, from both sides I am subtracting d minus yp by 2. So, actually I am subtracting d minus yp from d. So, basically this is equal to yp, right. So, I can rewrite this by substituting the value of yp by d, and then this is the equation I get. So, from here I can say m by mp is equal to 1 minus p by py whole square, okay, where mp for a rectangular section is sigma y b d square by 4, which we have already derived in the previous lecture. Okay. So, from the previous slide, this is the PM interaction. Often this m by mp we denote by little, this is denoted by little m, and this, as I will use later on, this is denoted by little p. Now, if you go to IS 800-2007, that is our steel design code, clause 9.3.1.2, let me show you what is the equation that we use in our code. Okay. So, you see here for plates, basically for rectangular section, this is the equation we use, m n d, which is basically the moment, that is this m here, m d is the design moment capacity under pure bending only, m n d is equal to m d into 1 minus n square. What is n square? The ratio of the axial force n by n t, that is p by py here. So, basically this same equation is used in the design code, where of course n d is calculated with the partial safety factor, m d is the design strength under corresponding moment acting alone. Okay. So, that you can take a look in clause 8.2, right. So, this is the same equation that we use in our design code, right. And often we need to use the stress resultant yield surface, which you will see when we go to plastic hinge modeling. Okay. So, we define the PM interaction, which is called the stress resultant, because axial force is a stress resultant, bending moment is also a stress resultant. So, this equation we can rewrite, because I said this is little m and this is little p. So, I can say m plus p square is equal to 1. So, this function is denoted by capital phi as a function of p and m, and this is called the stress resultant yield surface. Okay. So, if you plot this equation, you get that. Now, note that in almost all textbooks and in codes also, whenever we plot the PM interaction, we take compressive force to be positive and sagging bending moment to be positive, which is just opposite of what we were using for the axial force, right. So, you get this curve for that equation, right. Now, if you consider tensile axial force, then you will actually get the same equation. Okay. So, you can get that for the tensile. On the other hand, if you apply hogging bending moment and redo the analysis, you will get this curve, right. So, to capture all the quadrants, what I can do, I can actually replace this m by the modulus of m. So, that means my equation for the complete yield surface is going to be m plus p square is equal to 1, right. So, this is the stress resultant yield surface for a rectangular cross section. Okay. Now, I am sure all of you have done the steel design. So, if a point is within the yield surface, what does it mean? Your design is adequate, isn't it? Can it be outside the yield surface? The answer is no, because this is your capacity curve. You must be inside that, isn't it? So, the question is, how do we use it in nonlinear analysis? Well, we shall see in the upcoming lectures. Okay. So, now let me quickly show you an OpenSys example of determining the PM interaction for a rectangular section. So, how do we go about doing it? Let me first explain the idea. So, the idea remains the same. So, let us say I take this rectangular cross section, I will discretize it into number of fibers, okay, discretize it into number of fibers like so, and then what I will do, I will apply some axial force and then I will apply some curvature, which I will keep on increasing. Then I will get a moment curvature response for a given axial force. So, I will get m versus phi, let us say, which is something like that, right. And then this is for a given value of p, let us say p is equal to 100 kilonewton. I am just making up some number, right. And then what you do, you pick up the peak value, let us say this is the peak value that you pick up. So, you get corresponding this p is equal to 100, you get a value of the bending moment, right. Then what you do? Well, you change the axial force, instead of 100 you let us say apply 110, and then again you get another bending moment. So, you keep doing it for all values of axial force. Now, what are the values of axial force you will consider? Well, to do that, we know what is the Py of the cross section. What is the Py? If the width is b and the depth is d, okay, the yield strength of the cross section is b into d into sigma y, isn't it? So, I know my axial force will vary from 0 to Py. So, I can vary my axial force between 0 to Py and apply the curvature increasingly, get the maximum bending moment, and then I get P and M, and I can plot that. So, this is exactly what I have done in OpenSys. So, let me show you. Okay, I have run the analysis, right. So, how do you do this moment curvature analysis multiple times? So, what you have to do, the previous moment curvature analysis procedure, I have now put it in a module, in a Python module, and that is defined like this. So, definition DEF moment curvature Py2D is the Python module that I have written, where I am defining the node, fixing the degree of freedom, exactly the same thing as we have done, but now put inside a module, which I will be calling every time with some value of axial force, okay, and sending the maximum curvature, and then we will be applying that curvature incrementally and do a displacement control analysis as I am doing here. Okay. So, now let me show you where I am calling this function. So, this again this code is shared with you. So, here, so let us say I am applying this axial force varying between 0 and minus P y, minus indicates I am considering compression only, okay, and this is linearly I have taken 20 data points between 0 and minus P y, okay, and for each one of this axial force I am wiping the model, creating a model, and then defining the material with steel 01, defining the cross section, and then calling this moment curvature P y 2D module with that value of axial force for the ith and sending the maximum curvature, the number of increment, and from there I am getting the maximum bending moment. So, I am getting the moment curvature data and taking the maximum bending moment, right. So, if you do that, then you can plot the moment versus curvature. Here I have plotted in normalized space P by Py and M by MP, and I have also plotted the analytical solution which I just now derived. What is the analytical solution that I derived? Is this one, right. So, as you can see that OpenSea's and analytical solution are matching quite well. Okay. So, with that, let me summarize what we have done in this lecture. So, in this lecture we have looked at monotonic and cyclic moment curvature response for I section, okay, and we have looked at plastic analysis of rectangular cross section in the presence of axial force and derived the theoretical PM interaction curves, and I have also showed you that we use the same equation in our design code IS 800 2007. Okay. We have also discussed how you can develop PM interaction curve using OpenSeas using fiber section discretization. Okay. So, in the next lecture what we will do, we will look at the plastic analysis of wide flange section in the presence of axial force and look at the PM interaction curve. Okay. So, thank you.